Okay, hi everyone. My name is Jan, this is Ruslan, and today we'll be presenting Cobrix. So Cobrix is a Spark SQL data source for Mainframe and cobol. It was originally developed and open sourced by ABSA. So before we go into the technical details, I'll say a few words about who we are as a company. Then we'll touch on the business and technical motivations behind the project. Ruslan will then take you through Cobrix use cases and examples on how it could potentially help you guys as well. And then we'll take a step back and kind of see how Cobrix is used in the overall ABSA's data platform. So ABSA is a financial services provider, so it's a bank. It has business presence in 12 African countries. And it has a development center in Prague, which is where we come from. And when you look at the data engineering in ABSA, you'll see that Spark is very crucial to it. So we actually use Spark for many different purposes and in many different ways. But when we first started evaluating it as part of this big data team in Prague, we evaluated it as a technology of choice for building this new data platform. We soon found out that there were bits and pieces which were missing from the Spark and Hadoop ecosystem, especially if you looked at what we needed from the perspective of a regulated industry, the likes of strong metadata focus, data lineage tracking, capabilities to track the completeness and accuracy of your data as it travels through different data applications and so on. And this functionality didn't exist in the ecosystem at that stage. So this big data team that we work for in Prague actually looks for these gaps and bits and pieces which are missing, and we try to fill them. So we've done a couple of contributions to Spark, and we've open sourced a couple of Spark-related projects to help us build this overall data platform. So you can check it out on the ABSA GitHub repo. But you may have heard about Spline or ABRIS, which we presented previously on some of the previous Spark summits. OK, so in terms of the business motivation, I'm going to steal a quote from a colleague of ours who says that when people think of mainframes, they think of dinosaurs. But we find out that that's far from the truth. Especially in ABSA, it's still being actively used for most of the core banking functionality. And we found out reports, for example, in this article, they're saying that it's still being actively used by 71% of Fortune 500 companies. The mainframes process 87% of the world's credit card transactions. So in our opinion, it's a technology that is still relevant. We still need to get the data out of it to derive the value. And if you're like us, and if your organization depends on mainframes to a certain extent, and if you want to become a data-driven or data-centric organization, then what you could do is you could run your analytics on mainframes. So on, I think, IBM, you can run Spark. But with the mainframe cost model and licensing fees, running your analytics on the mainframes themselves could be quite expensive. So the way we look at it is we're going to extract the data from mainframes, and we want to ingest it in a scalable infrastructure like our HDFS data lake, where we've got Spark and so on, or potentially relational data warehouses and so on. So we looked at how this was done previously in ABSA, and we found out that there was this generic pattern. So people would use proprietary tools, proprietary ETL tools, to lift the binary mainframe file, episodic file from the mainframe, transfer it somewhere. You would then parse it and transform it into maybe a fixed-width format. And from the fixed-width format, you might do an extra little bit of work to get a CSV file. The CSV file could then be consumed quite easily by your data applications or ingested into your data warehouses. OK, but I've been mentioning a CSV as one of the middle steps here. So what happens with the likes of nested and complex types in COBOL? We still have equivalents of arrays and structures. This becomes quite tedious, right? And one of those transform steps in the pipeline would generally flatten these nested structs. So we would end up with a CSV of tens of thousands of columns, and it's just, it was horrible, and it was painful, and it was slow to process. In some cases, it was unusable. OK, so we kind of picked an example which we knew was causing a lot of headaches. It was ingesting some transactional data from a mainframe into HDFS. And this was a 600 gigabyte ABSA file. Using this kind of legacy process, using the proprietary tools that we had, the execution of this pipeline took 11 days. So we wouldn't be able to use the data in any sort of reporting applications or ML models until 11 days after it was produced. So obviously, that's not acceptable. So in terms of the technical motivation for Cobrix, we needed something that would give us better performance, that would be faster. We needed something that would be more flexible, that would allow us to deal with complex types and some of the advanced topics like variable length records or redefines in COBOL. And obviously, we needed scalability. So by the way, as a spoiler alert, when we implemented this same ingestion pipeline using Cobrix, we brought it down from 11 days to just over 1 hour. OK, so what can you do if you don't have a Cobrix, if we didn't have Cobrix, or what else could you use to do the exact same thing, to extract data out of your mainframes? Well, I already mentioned you could run Spark on mainframes. But that's going to be expensive, especially if you want to do machine learning, iterative algorithms, where you have to pay for a CPU cycle. That's going to become quite expensive. A lot of mainframe systems have integrations with streaming technologies like MQ. So what you could do is you could tap into those. You could parse the records, the messages which are being sent out of those mainframes, and you could try to make sense of the data this way. So there is a tool called Scoop. It's been around for a while. This tool might do fine for you if you've got very simple use cases. If you don't have redefines or variable length records or nested data types. In some of the more advanced ones, this could cause you quite a bit of headache as well. And of course, as ABSA, we've tried those proprietary solutions that I've mentioned. But maybe we were just using them wrong. But we found out that they were quite expensive. They were slow. They were complex. You required a lot of human power to actually, and a lot of expertise in those proprietary solutions. And it was quite hard to find. So how can Cobrix help you? So Cobrix gives you a lot of the functionality that you had to do in those intermediate boxes in the ingestion pipelines. So Cobrix gives you a lot of that for free. So obviously, it can help you decrease the human involvement and speed up the development of your ingestion pipeline. But also, it's built on top of Spark. So Spark has native, or Spark SQL has native support for structs and arrays and maps for nested types. So all of a sudden, we can deal with the equivalent types from COBOL natively in Spark. So it provides scalability. In some cases, this comes out of the box from Spark. In some cases, Cobrix needs to do a little bit of work on top of it. So Ruslan will give you more details about it. And of course, Cobrix is open source. So you can use it for free. You can modify it, change it, send us bug reports, and so on. OK, so I'm going to hand over to Ruslan now, who's going to do the more.
Hi, I'm Ruslan. I'd like to show you how you can use Cobrix to load mainframe files in Spark. So high-level overview of Cobrix. This is just another data source for Spark. So what you need is a mainframe data file, ABSA data file already on HDFS, and a schema definition file written in cobol language a copybook, and once you have it, you can provide it to Cobrix as a data frame. So we provide it to Cobrix, and Cobrix will help you to create a data frame. So it's built on top of Spark SQL API. So let's take a look of the kind of use cases we have. And what kind of transformations may be required in order to properly process mainframe files. So I'd like to introduce just a couple of mainframe terms in order to be able to understand what's going on. So the first two terms are a data file and a copybook. And the reason, like data file seems like just a file, but what's interesting about this project was a lot about communication between the teams and mainframe teams and big data teams, and we found out that by word file, mainframe people mean a different thing. So on mainframes, file can be a set of records that cobol application can query. So then such a file is copied to a GFS, for instance. A copying tool adds additional headers, so the file could be then read as a set of records afterwards. So even the word file is more complicated in mainframe world. So a copybook is just a schema definition from our perspective of loading mainframe files. So you can view a copybook as another interface definition languages similar to network protocols such as Thrift, Protobuf, and Aura. The difference is in design, of course, because the network protocols were designed to be flexible, schema evolution, simple types, and cobol is designed to be easily used in cobol for efficiency and efficient storage as well. So although cobol is very flexible in defining data structures, it supports, as was said, nested structures, arrays, and their combinations. The cobol format is very strict. So you need to specify how many bytes each string can have, how many maximum elements an array can have, and that sort of stuff. But when you have a copybook and a data file, in the simplest cases, then this mainframe file contains a set of fixed length records. Using Cobrix is absolutely simple. You just specify format as cobol to a Spark reader, and you provide a mandatory option, the location or the content of the copybook. And that's it. You have a data frame that you can process in Spark. And now comes mainframe-specific complications that you may encounter. So the first thing, mainframes have this notion called redefines. This is part of the schema definition. So what is redefine? A redefine is a field, or several fields, that can occupy the same storage and memory space. Why is it needed? So let's take a look at a small example. So imagine we have a database that contains a list of clients, and a client could be either a company or a person, but not both, just for the sake of this example. And you can see in this copybook on the slide that the company name takes 40 bytes, and first name and last name of a person takes 20 bytes each. So if we know that a record could contain either company or a person, we can save 30 bytes of space by redefining one field over another. So for every record, only one of the set of the fields can be meaningful. And this is a concept similar to unchecked unions, variant types, and you can see in other languages. So what can we do about it? So unfortunately, cobol itself does not provide a formal way to define which redefine to use in which circumstances. So usually when you are given a copybook, it contains a lot of comments about when to use one redefine over another. And Cobrix is not at that stage yet to be able to parse comments. So we're kind of in a situation that sometimes I get the feeling that compiler ignores all my comments, sort of thing. So what Cobrix does is that we try hard to parse everything as if every redefine is valid for every record. And we get a data frame that contains fields that may be kind of don't have semantic meaning, I would say. So in order to be able to clean up such a data frame, we need to apply application level logic. In this case, we have this useful Boolean is company that we could use. You can use very simple Spark code. I won't even stop on this slide very long, just to set nulls for fields that don't make sense for particular type of record, and leave the field if it can make sense, have semantic meaning. So a redefine is a very important concept when you want to load data from hierarchical databases. So what's a hierarchical database? Hierarchical database models were heavily used in 60s, but then in 70s superseded by relational models. But hierarchical models are still widely used today. So what's hierarchical models? Hierarchical model is keeping data as a tree of entities, and each level of entities has its own schema. Like in this example, imagine we have a database of the companies, and each company can have 0 or more contact people. So a company is what's called in mainframe terms root segment or root record type, and contact person is the child segment or child record type. So hierarchical database keeps parent-child relationship automatically for you, and you can query this database from a mainframe. But again, when such a file, such a database, is copied from a mainframe to a PC, the copying tool kind of serializes, I would say, maybe appropriate word for, taking all of the records and making a file as a sequence of records, which are order dependent. So such a file always starts with a root segment record, followed by several child segments. And then again comes root record as well. So copying tool adds usually additional headers that will enable you to distinguish the sizes of the records or sometimes record types. So such a file is sequential by nature because each record has only information about itself. You cannot read such file in the middle, which is one of the obstacles we'll talk about later. So in order to read such a hierarchical database file in Cobrix, what you need to do is first to construct a copybook that would contain schema for the parts that are common across all segments. So in our case, we have two fields, segment ID and company ID, which are present in both segments. And then comes struct types, or in mainframe terms, groups, that contain segment-specific fields. So in our case, company is a specific struct field for a company segment, for a root segment, and contact is a field specific for a child segment. So when you have such a copybook, and it's very important that those segment-specific fields redefine each other. So you see contact redefines company. So when you have such a copybook, the only thing you need to do is just add additional option to a Spark reader for Cobrix. It's is record sequence equals to true. And in this case, Cobrix will use the standard RDW headers to read files and split them by records. So that's the only thing you need to do in the simplest case. But again, you will end up with a big data frame that contains every record, no matter which segment each record belongs to. So again, we'll get invalid values for fields that don't match the segment. So we'll see if segment ID is C, it's a company, so company field is valid, but contact probably invalid. Not probably, it is invalid. And for segment, if segment type is P, person, we see that contact information is valid, but company is invalid. So what can we do about it? And another approach that we could use besides filling the data with nulls is we can split the segments by separate data frames. We can use Spark for that, so we can filter by segment types and we can select fields that are meaningful for a particular segment. So we'll get, in this case, if segment ID is C, we just get in the list of companies. And we can do the same for child segments, but this time we'll use Cobrix specific predicate pushdown. So we can specify an option for Cobrix segment filter equals P. When you do that, Cobrix will filter out segments during the parsing time. So it won't parse all of the segments. It will just keep records that for which segment doesn't match. So it will work faster. So you can choose which way to split the tables. And then you have this. When you have those two tables, if your target is a relational data warehouse, you can just put those tables into the warehouse. But if your target is a document storage, probably the logical step will be to denormalize the data by joining the tables. In our cases, we are joining by company ID to have this big denormalized table. And once we have it, we could use Spark to group by root segment and collect list child segment. So we could have a nice document type data which contains company fields in the root level and contact people as a nested array, which is absolutely natural for Spark and for document storage. But you probably would ask me, like, if you see only this, you would ask me that my example was kind of biased because it had company ID field, which allows us to join those segments and combine them into one big table. But usually, hierarchical databases do not contain such fields because hierarchical databases maintain parent-child relationship automatically and doesn't need auxiliary tables to do joining. So let's take a look at this example. This is the same example as we saw before, but no company ID field that is present in both segments. So Cobrix can help you here as well using ID generation. So basically, simply speaking, it can generate company ID for you. So in order to do this, what you need to do is just to specify which field of your copybook is a segment field, segment identifier, which values of the segment belong to root level, which is the second option. So in our case, it's C because it's company. And the third optional option is a segment prefix that lets you control the structure of ID in case you want IDs to be repeatable, non-repeatable for each Spark job, depending on your ingestion needs, I would say. So when you do this, you'll end up with a data frame that looks exactly like in the previous example. And this seg0 ID field is generated one. It absolutely has the same semantic as company ID, so you can do all of the splitting and joining afterwards. So also you may ask why it's called seg0 ID, why not just, I don't know, parent ID. And that's because hierarchical databases can contain multiple levels of hierarchy. So child segments can have children of their own, and so forth and so on. And Cobrix can help you generate IDs at every level, so you could restore parent-child relationship. And there is one additional option that you can use, which allows you to increase performance, especially if your copybook contains a lot of segments. So in our example, we had only two segments, root segments and a child segment. But what would you do if your copybook contains dozens of segments? So it will work, but it will work slowly because Cobrix will try parse every segment for each record. So you can speed up the process by providing the mapping between redefined field name and the segment ID. I won't go deeply into details about that. You can look at the documentation, but it's very important that you know it. And if you have dozens of segments, it will speed up the process by a big extent. So speaking about performance, remember that we looked at this file, hierarchical file, and then it's copied to HDFS from a mainframe, we saw that it's naturally sequential. So each record contains a header specifying the record size, so you can read first record, second record, and so forth and so on, as long as you read previous record. So you cannot just read file in the middle, because it's a binary file, you cannot find a distinguisher. You don't know where each record starts. And if you apply naive logic of parallelizing this in Spark, you'll get the very slow constant throughput. Like here in our lab cluster, it's just 10 megabytes per second for processing mainframe files. And you may wonder, if there are millions of such files, that's no problem. Spark can parallelize those files for you. But usually, like in our use cases, we have just one very, very big file of 600 gigabytes. So it's no good to process it sequentially. So what can we do? So to solve this problem, we used what we called three-phase processing. So at first stage, we read quickly through the file without parsing data, just getting headers and locations for each record. And we construct a sparse index. This sparse index doesn't contain the locations for each record, but only records that are on the partitioning boundary. And partition size is determined by HDFS block. So we construct the sparse index. This is the first stage. The second stage, for each of the block of our sparse index, we ask HDFS, please give us the locations of those blocks of files, of those offsets of the file, which data nodes it contains. So it's used for data locality awareness. And the next step, we use sparse index to repartition the job according to the size of the file and provide data locality hints to Spark, so it processes chunks of the data as fast as possible. So when we applied all these optimizations on our lab cluster with 4 nodes, we achieved quite a good performance. And you see these graphs demonstrate that the bigger file you have, the more advantage you have of using more Spark cores to process it. So actually increasing the size or input size of the file and gives us ability to increase the number of executors. So this graph shows that the process, not only it's high performant, but it's also scalable. And this is also an interesting comparison, which we are quite proud of, because on the left side, you see the processing speed throughput for a fixed length file when we don't need to build sparse indexes and provide data locality. Spark does everything for you using binary records interface. And on the right side, we see processing a variable length file, which uses all those optimizations techniques. And the variable length file performance is just slightly slower than the one from the fixed length record files. So it's so we're proud about this result. OK, and I'm going to Jan.
So let's take a step back and let's have a look how Cobrix is used in this wider data platform that we're building in ABSA, and how it collaborates with some of the other tools that we open sourced for the Spark Hadoop ecosystem. So at the moment, well, it's not really at the moment. I think this slide is a bit old. But at the time of writing this presentation, we've had just around 180 data sources being consumed on an everyday basis from mainframes using Cobrix in production. The way it works is Cobrix can't really help you with the extraction of the binary file from your mainframe. So at the moment, we are still dependent on proprietary tools to do that. But once we've got a binary episodic file which is landed in HDFS, we use Cobrix and Spark to kind of parse it, load it into a Spark data frame. We're also targeting to build a data lake which has clean and ready to consume data. So that means data which is ready for consumption by both regulatory reports and by data applications, ML models, and so on. So it's important for us to have certain confidence in the data quality and the fact that the data conforms to a certain schema, that we've got data lineage, data documentation, and so on. So to do that, we use another project that we open sourced called Enceladus. We call it also conformance engine. So it's an engine which conforms the data into kind of globally understandable form or language, if you want. So at the same time, we've got regulatory requirements to capture and have data lineage available for, especially for risk reporting. But yeah, we've got a tool called Spline, which kind of automatically captures data lineage of Spark SQL jobs for you. So this is used in Enceladus to capture data lineage for us. So this is the batch world, and this has been around in ABSA for a while, but we're also looking into streaming. So it's a similar type of ingestion pipeline, except that instead of HDFS as your storage and distribution medium, we use Kafka. So basically, we would use the streaming capabilities in some of the mainframe systems that we have, like MQ. We would read it using Spark and Cobrix to parse the records into data frames or streaming data frames. We've got this tool called ABSA. So we call it a bridge between Spark SQL data frames and data frames of binary Avro records. So this is for interoperability with other systems. And ABSA also has a full Confluent support. So if you are using the cool features around Kafka and streaming, like the schema registry, ABSA can help you with that. OK, so here you can see Enceladus as well. So Enceladus is written on top of Spark SQL. So we will do a little bit of work to ensure that it works nicely and properly on structured streaming. And that way, we can have the data conformed using exactly the same code from both the batch and stream pipelines. So if you combine these two pictures together, you'll see our take on Lambda architecture in ABSA. And this is what it kind of looks like when you combine those two worlds. OK, so before we finish up, a big thanks goes to our colleague Felipe, who is the co-author of the project. Unfortunately, he couldn't be here today, so I am substituting. And there's a lot of other people on the slide that made this project possible, so a big thanks goes to everyone on the slide. And finally, we are open source, so we would love you guys to have a look at the project. Use it. If you find bugs in it, please report them. If we're missing something, request a feature. And if you're brave enough to submit a pull request whenever you're in Prague next time, we might invite you for a beer. OK, so I think that's it from our side. And if you guys have any questions, we'll be happy to answer them.
Yeah, if you've got any questions for Jan and Ruslan, there's a mic there.
Hi, I have a question. So while you're doing your batch processing, is that always truncate and load, or you guys are doing some kind of incremental load as well?
So especially for the likes of transactional data, where you've got quite a large history of data, when you look at the binary episodic files, those might be quite massive, right? If we're dealing with a history of, I don't know, say a couple of years. So what we do in batch is we do a once-off ingestion, or that's at least the plan, do a once-off ingestion in batch, and then continue building up those snapshots in a streaming way. Does that answer your question? OK,
all right,
great.
yeah, no, thanks again. And make sure to go on to the Spark AI Summit app and rate the talk.
Great,
Cheers.
thank you.